78 meters below the ocean floor through 28 distinct geological strata, China is boring a high-speed rail tunnel that conventional engineering says should not exist. It is not even the most extreme. 123 kilometers across the Bohai Strait through active seismic faults at a projected cost of $36 billion. 4 underwater tunnels each push past limits the industry once treated as absolute. Jintang and Zhanjiang Bay, their names now stand for a new threshold in tunnel engineering along China's coast. At Jintang, the tunnel drive plunges to 78 meters below the ocean floor, cutting through a labyrinth of 28 geological layers. Each layer brings a different challenge: soft marine clay, abrasive granite, fractured sandstone. The solution is not a simple cutter swap, but a machine armed with 308 custom-designed cutters, each one engineered for a specific slice of the earth. The tunnel boring machine, stretching 135 meters in length and weighing 4,350 tons, operates under conditions that would have halted older projects. Engineers must maintain thrust and alignment as the cutter head transitions from one stratum to the next, all while resisting a water pressure that can reach 8.5 bar, enough to crush a steel drum in seconds. The Zhanjiang Bay project further south takes a different gamble. Instead of the standard two-headed approach, digging from both ends to meet in the middle, engineers chose a single-head TBM, a tunnel boring machine. This machine, with a diameter of 14.33 meters, is designed to withstand 5.2 bar of hydrostatic pressure beneath 52 meters of seabed. The decision for a single head is driven by the unpredictable fault zones in soft soils, where even a small misalignment could derail the entire operation. The cutter head is built for rapid reconfiguration, able to adapt to 4 major soil types without pausing the advance. Along the tunnel wall, redundant pressure sensors and real-time navigation systems monitor every shift in the ground, holding the line against collapse. In both projects, the numbers are staggering: hundreds of cutters, dozens of strata, and water pressures that test the limits of steel and concrete. Conventional tunneling theory would call for a halt, a redesign, or a retreat to safer ground. Here, engineers move forward, building machines and protocols that did not exist a decade ago. The pressure to succeed is not just physical, but national. These tunnels are the first links in a chain meant to bind China's coastal cities into a single high-speed network. The Yangtze River Tunnel does not cross open sea. It faces a different kind of pressure, nearly 100 meters of riverbed, with shifting currents and silt that can swallow whole machines. Here, a 15-meter diameter tunnel boring machine, the largest ever deployed for a high-speed rail river crossing, ran almost non-stop for 2 years. The drive covered 11.2 kilometers under the river, maintaining a daily advance rate that at its peak reached 30 meters per day. The engineering team had to keep the cutter head perfectly aligned, adjusting for millimeter deviations as they passed through layers of soft clay, sandstone, and basalt. The project's $72 billion corridor budget covers not just the tunnel itself, but an entire east-west high-speed artery spanning 2,000 kilometers. Scale takes on a new dimension at the Bohai Strait. The planned tunnel will stretch 123 kilometers, longer than the Channel Tunnel and Japan's Seikon Tunnel combined. Its design calls for 3 parallel tubes, 2 for high-speed trains, and a central gallery for emergency evacuation and maintenance. The projected cost is $36 billion, and the route must cross 4 active seismic faults, each capable of generating earthquakes above magnitude 7. To survive these conditions, engineers have specified ductile steel concrete segment joints that can flex and absorb up to 30 millimeters of movement. The tunnel will run beneath water depths reaching 110 meters, with hydrostatic pressure and fault displacement that push the limits of current TBM technology. Both projects force a rethinking of what a tunnel boring machine can do. The Yangtze's continuous 2-year drive set a new benchmark for uninterrupted excavation, while the Bohai's 3-tube fault-crossing design challenges every convention in subsea engineering. Together, they complete a catalog of projects that would have seemed impossible just a decade ago. The tunnel boring machines at the heart of these projects are not simply large, they are colossal. The Jintang tunnel boring machine, for example, stretches 135 meters from cutter head to tail and weighs in at 4,350 tons. That is the mass of a fully loaded Boeing 747, moving not through air, but through rock, clay, and seawater. The machine's thrust system delivers up to 45 meganewtons, enough force to lift 7,000 elephants, yet all of it must be applied with millimeter-level precision. Operators monitor the machine's position in real time, using a guidance system that tracks deviations as small as 2 millimeters over a tunnel radius of more than 7 meters. If the cutter head drifts even slightly, the entire tunnel could veer off course, risking catastrophic misalignment. Inside the pressurized shield, the environment is closer to a deep-sea habitat than a construction site. Hyperbaric chambers allow maintenance crews to enter the cutter head zone without depressurizing the face. A typical cutter swap, removing worn steel discs and installing new ones, takes just 45 minutes, even at depths where external pressure can reach 8.5 bar. The logistics are relentless. Spare cutter cassettes are staged in pressure-controlled depots, and a dual crane system moves them into position with no margin for error. Every component, from the hydraulic actuators to the fiber optic telemetry lines, is engineered for both brute strength and surgical accuracy. The scale of these machines is matched only by the demands placed on their operators. A tunnel boring machine driver sits at a control panel surrounded by screens streaming data from hundreds of sensors, bearing temperatures, face pressure, cutter wear, and alignment metrics. Any anomaly triggers an immediate protocol, whether it is a shift in ground composition or a spike in water ingress. In this environment, the difference between routine progress and disaster is measured in seconds and millimeters. The hardware is immense, but the discipline required to keep it moving is even greater. Pre-staged cutter inventories and digital twin oversight now define tunnel performance. Spare cutters stored in pressurized depots are swapped in under 45 minutes, even at depths reaching 8.5 bar. In the Yangtze River Tunnel, shift leaders preloaded enough cartridges for 72-hour cycles, keeping the tunnel boring machine known as TBM moving through unpredictable geology. Downtime that once stretched for hours has been compressed to minutes. Each tunnel is paired with a digital twin, a virtual model that tracks cutter wear, face pressure, advance rates, and torque. When the Yongxing TBM set a 510-meter record in a single month, it was predictive modeling, not just brute force, that flagged cutter fatigue before failure. The digital twin's emergency engine simulates stalls and water inflow, triggering protocols and pre-approved plans. These methods push past standard limits. Earth pressure balance machines are rated for 60 meters, but engineers now drill at 78 meters in Jintang, 84 meters in the Yangtze, and aim for 110 meters in the Bohai Strait, depths once considered off-limits. In Zhanjiang Bay, the shift to a single-head TBM, breaking from the orthodox two-head design, has drawn both skepticism and admiration. The chief engineer's team rapidly reconfigures cutter modules, maintaining a constant feedback loop between the digital twin and field crew. Every deviation is logged, and if successful, becomes protocol for future projects. The results are 260 meters per month as a stable average, 510 meters in a record month, and routine operation at pressures that would have halted work in any previous era. Risk is managed by a choreography of logistics, automation, and human oversight. Travel time on these underwater corridors is not measured in minutes saved, but in entire journeys erased. The Jintang Tunnel cuts the Zhoushan to Ningbo trip from 90 minutes to just 26. The link to Hangzhou, once a 3.5-hour ordeal, now takes 77 minutes. Dalian to Yantai, a 6-hour slog by road and ferry, drops to 40 minutes by rail. Guangzhou to Zhanjiang, once 5 hours, is now 90 minutes. These gains are not theoretical, they are built into the concrete and steel of each tunnel. Every route is engineered for resilience. Ductile steel concrete joints flex up to 30 millimeters, absorbing fault movement that would crack ordinary linings. Elastomeric rail mounts, tuned to 1.2 megapascals, dampen shock and vibration, preserving track alignment at 250 kilometers per hour. A central gallery runs the length of each tunnel, providing a redundant escape and maintenance route, ensuring that even in the worst-case event, trains can keep running or evacuate safely. The payoff is not just speed, but a network designed to survive what the sea and earth can throw at it. No underwater high-speed rail tunnel exists in the United States. The Gateway program, set to replace the aging Hudson River Tunnel, began planning in 2013 with an initial budget of $12.2 billion. By 2025, the price tag had ballooned to $21.9 billion, and the opening date slipped from 2029 to at least 2033. California's high-speed rail project followed a similar pattern. Approved in 2012 at $33 billion, it now sits at $80 billion, with the first phase delayed to 2045. In the same period, China's Ministry of Transport set a target of 50,000 kilometers of high-speed rail by 2030, a network unmatched anywhere in the world. While the U.S. navigates audits, funding gaps, and shifting timelines, China is building underwater corridors at a pace that redefines what is possible in rail engineering. Today, crews drive 4,500-ton tunnel boring machines through 28 pressure zones, under 7.8 megapascals of water, where a millimeter error means disaster. As China pushes these limits, the boundaries of engineering shift. The impossible is recalibrated in real time. This is not just ambition, it is a new definition of possible.